We'll be having the technical session 3 by Mr. Arjun Menon, the Chief Engineer from InCore Semiconductors Private Limited. To introduce Arjun Menon, he's the co-founder and Chief Engineer of InCore Semiconductors, and he was one of the key architects of Shakti processor program at IIT Madras, and was very instrumental in designing India's first indigenously developed RISC-V processor. While working at IIT Madras, he was the lead architect of a 64-bit out-of-order processor based on a custom ISA designed for one of India's strategic agencies. He was also the tech lead for custom SoC for ISRO Initial Systems Unit. He received a BTech in ECE from Amrita School of Engineering and an MS in Computer Science from IIT Madras, mentored by Professor Kamakoti, the director of IIT Madras. Over to you, Arjun Menon.
Thank you. All right. So today I'm going to be talking about something called secure boot. We would, of course, not try to go into many implementation details or nuances of how the maths behind all of this works, but just try to understand at a high level what secure boot means, why do we require it, and how do we implement that. Before we begin, let me give you a quick introduction about our company. We are InCore Semiconductors. This company was formed by people from the Shakti team at IIT Madras. So once we went ahead and designed, 2 processors or did 2 tape outs at Shakti, we found that there is a lot of traction from a lot of agencies in India and abroad who are looking to adopt RISC-V and design custom silicon. And hence, it made commercial sense to go ahead and start a company that can cater to all of these needs. InCore is a RISC-V solutions company. So if anybody wants to design their own custom silicon based on the RISC-V architecture, that is something that we would take up. We are primarily targeting the embedded domain. Again, if you look at our product portfolio, we have multiple RISC-V core generators, right? We call them core generators because it is not a single instance of a core. You would have multiple different configuration parameters to choose from, and based on these parameters, you would get a core that is very much tailor-made for your application. If you look at the RISC-V instruction set itself, it is very modular. So you can pick and choose certain instruction sets that are targeted for your particular application. At InCore, we support all of the configurations that RISC-V supports and something on top of it, which account for various microarchitectural features. We also have various fabrics and interconnects like AXI, AXI4 Lite, APB, etc. We also design certain accelerators like accelerators for cryptographic algorithms and other uncore components like interrupt controllers and low-speed peripherals like UART, etc. Finally, we offer custom silicon services for people who want a bespoke silicon. For example, may be adding new instructions to your processor or designing accelerators for your particular application. We also act as a one-stop shop for end-to-end custom silicon needs, and that's where our partner network comes in. So if somebody wants to do right from spec to RTL design, backend, placement, routing, all of that, test tape outs, mass scale production, board design, followed by software support, all of this, we would act as a one-stop shop along with our partner networks with companies like HCL and Tessol, to name a few. Finally, we are backed by Sequoia, which is now called Peak 15. With that, let's look into what is secure boot and why do we require it, right? So let us say you're trying to run a program on a particular hardware, right? How do you know if the program that you're running has not been tampered with? Or how do you know if it is it is being provided by the right vendor or the right source of a person. Finally, how do you protect your secret code and data that is present in the executable, right? Secure Boot tries to solve all of these problems, and in order to, unless your code actually passes all of these tests, you will not allow the code to run on your hardware. So the way we will be looking at this is by forming multiple levels of abstraction. We would look at what hashing and encryption mean. That is the most basic level of operations that will be used. And then using these concepts, we will build what is Diffie-Hellman key exchange and what do you mean by digital signatures. We would then use these concepts again to form various APIs that the Secure Boot code will use, and then see how you can use those APIs to actually build a Secure Boot flow, right? So what is hashing? It is a mathematical one-way function that basically transforms some data into a fixed length of bit strings, right? So if you look at this example here, you have two strings, and the only difference between these two strings is that the last full stop is replaced by an exclamation mark. Now you'd see that if you compute the hash function, which in this case is called SHA-256, the values are entirely different, right? So it is impossible to determine what the message is just by looking at the hash. And that's why it is called a one-way function. The second is called encryption. You would use encryption if you want to obfuscate data. So the typical operation would look something like this. In any encryption algorithm, you would need something called keys, right? So the encryption function would look like that, where you would pass your data along with a key and you get some encrypted data. This encrypted data would not make sense to somebody who would not have something called a decryption key, right? So if somebody has the decryption key called K2, you can then make sense of D of E, and you can get back D prime, which will be equal to your actual data. Now there are again two types of encryption algorithms, symmetric key and asymmetric key. If both the keys that are used for encryption and decryption are same, you would call them symmetric key, and otherwise you would call them as asymmetric key algorithms. Now the advantage with symmetric key is that they have very low latencies and you would have high throughput. It is typically used to encrypt very large amount of data. Of course, the assumption is that if you have a single key, you are supposed to keep that key secret and you're not supposed to give that key out. In asymmetric key, however, the encryption and the decryption keys are different. So it is all right to release one of the keys to the public and just keep one thing to your private. So almost all encryption algorithms would have something called a public key and a private key. Now, of course, the advantage is that you can still give out one key. We'll see how we use this to do key exchange. But again, the asymmetric key encryption algorithm is typically used to exchange very small data bits. So you can use an asymmetric key algorithm to exchange and get a symmetric key, and then use symmetric key to transfer very large chunks of data. So let us look at what Diffie-Hellman key exchange means. So let's say two people called Alice and Bob want to exchange some information, right, through an unsecure channel. So whatever you send through unsecure channel is something that people can read and decipher. So Alice and Bob, both of them have a pair of keys called the public and private key. We will be using an asymmetric key algorithm here. The way it works is both of them exchange their public keys with each other, right? And that traverses through the unsecure channel, which is fine because they are public keys. They retain the private keys to themselves, right? And then they try to combine both of these keys to form a single shared key. Now, using this particular shared key, you can obfuscate some data. So Alice uses her public key or her shared key to obfuscate a data, and that obfuscated data is sent through the unsecure channel to Bob, who can decipher that using his shared key. So this is how you would exchange information between two parties through an unsecure channel. Finally, we have one of the most important concepts that we'll be using in Secure Boot. It is called digital signature. Just like your physical signatures that marks the authenticity of, let's say, a document that you sign, digital signature tries to authenticate certain data or code that you would want to send to somebody, right? Again, there are two parts of digital signature. The first is called the signing part. In the signing part, what happens is you have two inputs. One is the data that needs to be signed, and the private key of some asymmetric key algorithm, right? The operation is very simple. You compute the hash of the data, and then you encrypt that hash using the private key. And the output that you get is called the signature. At the verification side, what happens is you would have to provide the data along with the public key and the signature. And the person performing the verification would again compute SHA of the data. It would decrypt the signature using the public key, and then match if Y and Z are same. Now note that I have mentioned here that the signature generation happens on the host side and the signature verification happens on the target side. What we mean by that is if you're trying to program a microcontroller, you would typically write an application on your laptop or on your PC, compile it, and transfer that executable onto the microcontroller, right? So in this scenario, your PC or your laptop is the host and the microcontroller is the target. All of the operations of signature generation has to happen on the host, right? So the host will basically take care of generating an executable along with the signature, and it passes that information onto the target, which is your actual controller, which will perform the verification. So with these two concepts, let's move on and try to understand what are the various components of Secure Boot. The very first thing are indeed the keys themselves, right? You would have to store certain public keys in the hardware. Of course, you just don't store one single key. You would want to store multiple keys, because if you lose or if one key gets compromised, you still have other keys to work with. And these keys, they're stored in hardware fuses. Hardware fuses are very similar to your physical fuses in the sense that once you burn a fuse, you can never get the older value back. So by using hardware fuses, you can make sure that once you've burnt a value onto this fuse, it can never be changed by anyone else. So that is how you ensure that the keys are not tamperable. And the collection of these keys, in some sense, form the hardware ID. The second important component is the boot ROM code. The boot ROM code is what is actually responsible for performing all the operations, like installing a new key or verifying the signatures of the code or data or whatever it is that you would want to. And finally, decrypt any information that is present in an encrypted form in the device. There are also certain other components, one of them being tamper detect. What if somebody tries to physically tamper your chip and tries to access information out? So you would have some mechanisms which will detect physical intrusions, and based on that, you would take certain actions like deleting keys or deleting secret information and resetting the processor. You would also have an on-chip memory. So in some threat models, people might not trust data that is sitting anywhere outside their chip. For example, an external DDR memory, right? There have been many attacks based on DDR memories. So people might not want to put secret data on an outside memory, and hence it is important to have some level of internal memory to store very critical secret data. Finally, you also have accelerators for cryptographic algorithms, be it any of the algorithms that we saw like SHA, RSA, or AES. You would require cryptographic accelerators for two reasons. One is, of course, for performance. The second is to prevent side channel attacks. If you've been following the news lately, there have been a lot of side channel attacks that have been happening, and they are much easily preventable by using hardware accelerators rather than trying to solve them in the software domain. So if you look at the hardware of course has all of these keys. The SRKs are basically super root keys. These are the keys that are fused onto the hardware. These are the public keys, along with the other components that we talked about. You can see that there is a RISC-V core and there's something called PMP there. We would touch upon that towards the end of the talk. But if you look at the software side, software basically refers to the memory, right? The memory would have multiple such key store tables. There's something called a public key store table where you would install various public keys. And there is also a symmetric key store table which installs your symmetric keys. Finally, your boot ROM code, of course, needs some stack space to execute. That is also part of your memory. And it is important that all of these three things are also not tamperable. If you look at the flash, right, that is where your actual executable is present. The actual executable will again have two components. One is the program and the command sequence file. The command sequence file is what tells how do you basically go about verifying this executable. Which keys should you install and which keys should you use to verify various signatures. Right. So let us now look at some of the APIs that Secure Boot requires. The very first one is the install public key. This is very similar to the digital signature that we saw previously. So you would have a key that is to be installed along with another key. So if you remember the digital signature, we were trying to verify digital signature of some data. That data can be anything. It can be a program, it can be another key, right? So this API basically talks about what if that data is a key, right? So you're trying to verify the signature of one key using another key that is already installed. So the functionality is very similar to the digital signature again. You compute SHA of the key. You again read an existing installed key from the public key store table. You use that to decrypt the signature and match if the results are equal. You also have authenticate data or program. This is exactly like digital signature. You try to verify if the signature of your data or your program is valid. The third is install secret key. Secret key is the symmetric key. So you would have an encrypted key that is provided. You would decrypt that encryption key using one of the symmetric keys that you have installed. So the only difference between the first and the third is that the first one was a public key, as in it was an asymmetric key algorithm, and here it is a symmetric key algorithm. Finally, you have decrypt image. You would basically use one of the symmetric keys that you have installed to decrypt the image that you have. With these four, let us finally look into how you would actually go about performing secure boot, right? If you look at the signed image, you can see that there are a couple of components there in the command sequence file. First is the list of API calls. We would be calling these APIs one after the other. And then you have something called a CSF key. The CSF key is what is used to sign the command sequence section. So it is important to make sure that the command sequence file is not tampered and the executable is also not tampered, right? So you would have to verify two different signatures. In order to verify the first signature of the command sequence file, you would first install a key, and that key is present there. After which, the signature of the command sequence file is present and the signature of the actual executable is present. So the very first step is to install the public key, which is the CSF key in this case. Once you have installed the CSF key, you can use that to authenticate if the CSF has not been tampered with. Once you authenticate the CSF, you would then go ahead and execute the third instruction in the CSF, which says you have to authenticate the data. That means the entire program, the code, and the data of the actual executable. Once that is verified, you can basically load the program and execute it. Now, what happens if I want to support an encrypted boot flow, right? If I want to make sure that the image that I have is not readable by anybody else other than just this processor, you would have to encrypt your entire program. Once you have done that, what happens in the secure boot flow is the first 3 steps are same, but before you execute the program, you would have to install the key that can decrypt the program, then go ahead and actually decrypt it, and then execute the program. Finally, it is really important that once you install these keys in the public key store table or the private key store table, you have to basically make sure that these keys are not tamperable, right? If you have to use those keys for in further authentication. And that is where RISC-V comes into picture. RISC-V has a feature called physical memory protection. Just like your normal systems, right, where you have your operating system and a user program that is running, both of them run at different privilege modes. So what RISC-V allows you to do is you can define that certain privilege modes can have certain read-write accesses to predefined regions of memories and prevent accesses from user-level code. So in RISC-V PMP, you can basically go ahead and say that if your keys are stored between 10,000 to 20,000 hex, you can define an entry saying that from 10,000 to 20,000, I would allow only machine mode to perform read and write, and I would not allow user programs to read and write. That way you can make sure that only machine mode has access to this, and mostly machine code is part of your trusted code. Right. So how do you actually use secure boot, right? What we talked about right now is just loading one program, but in an actual system, you would have programs getting loaded one after the other, right? Like you would have a bootloader that loads the operating system loads applications, and so on. How do you make sure that none of these things are tampered with? All of this starts right at the hardware level, and that's why the hardware is called the root of trust, which is basically the set of all the fuses that are present in the hardware. The hardware then first verifies and loads the bootloader. The bootloader in turn uses the secure boot APIs and then verifies and loads the operating system. The operating system again uses these APIs to verify and load the application. So in this way, you can, starting from the hardware, you would go about building trust in your entire boot process. And that is how you would secure your entire stack. With that, I would like to conclude. We are hiring, so please visit our booth or visit our website for further information. Thank you.
Thank you, Arjun Menon. May I now request Dr. Shankar Raman to felicitate Arjun Menon with a memento.